example. This example, a slider crank mechanism is used to impart motion to the base of a spring mass damper system, as shown, approximating the base motion yt as a series of harmonic functions. Find the response of mass for m is equal to 1 kilogram, the mass of this particle. The damping constant is 10. The stiffness of the system is 100 Newton per meter. This radius of this shaft or crankshaft is 10 centimeter. The length of this link is 1 meter. And finally, the frequency of the rotation for this crankshaft is 100 radian per second. Here you can see the motion of this crankshaft or this shaft with length r is a harmonic motion, but due to this link L, which converts the rotational motion into a translational motion similar to the engine of a car, we have the same mechanism which converts this harmonic motion into a periodic translational motion. So here we deal with a periodic translational motion yt. As you can see, this is the displacement yt. And now we can find a relation between this yt and this rotation omega, the angular rotation omega t. And then once we find the yt as a function of omega t, we can extract a harmonic form for the base excitation, and then we can write the equation of motion for this system. Includes mass m, stiffness, a spring with a stiffness k. Here we have two springs with the stiffness k divided by 2 or half k. So the total stiffness for this system is k, and also the damping c. So in this system, we have one base excitation, and we call it yt, and we need to find a relation between yt and this theta rotational motion. If we consider another angle here, phi, this is the angle of this link with length L with respect to the horizontal surface. So this angle phi, now we can write the yt as a function of phi and theta, because if we assume that the origin point for yt is when this arm R and this arm L are in the horizontal conditions, so yt will measure from this position, and we can find that yt is equal to R plus L, which is the initial length when both these two links are in horizontal condition. I mean, for example, something like this. This is the pin connection, and then this is the initial position for y. It means that at this condition y is equal to 0. And now if we want to measure the y, it's equal to R plus L minus R cosine theta, which R cosine theta is this length. This is R cosine theta, and minus L cosine phi, which L cosine phi is this length. So from these triangles and from the trigonometry relations, we can find out that yt is equal to R plus L minus R cosine theta minus L cosine phi. And also we know that cosine phi squared plus sine phi squared is equal to 1. And from these two triangles, let me change the color. In this triangle and this triangle, the blue one, and this green triangle, in these two triangles, if you compare this length here in the blue triangle, this length, this one, this length is equal to r times by sine theta. And if you write this length in the green triangle, it's equal to L times by sine phi. So r sine theta is equal to L sine phi. And also we know that cosine phi squared plus sine phi squared is equal to 1 from the trigonometry identities. Or we can write that cosine phi is equal to square root of 1 minus sine phi squared. And finally here, instead of sine phi for this term, we can substitute from here that sine phi is equal to r divided by L times by sine theta. And finally, in this equation, instead of cosine phi, we can substitute this term, this phrase. And now, if you substitute, you can see that yt is a function of only theta. So, because this is a single degree of freedom system and there is a relation between phi and theta, and we can find this relation using the trigonometry identities. So yt will be only a function of theta, which theta is equal to omega t. So by substituting theta is equal to omega t, you can see that y is a function of time finally. So this is yt r plus L minus r cosine theta minus L times by square root of 1 minus cosine, sine phi squared, or instead of sine phi, we can substitute as a function of sine theta. Now we can simplify this equation to extract the harmonics for this yt, because here we have a square root, and to find the particular response for this non-homogeneous term, it's a little difficult to obtain a particular response. So still we need some simplifications to simplify these equations. Is it clear so far?
Yes, sir.
Okay. So the next step, we need to obtain another relation for the phrase under the radical here. So for this phrase, we need to find another estimation. So here we can assume 1 minus this term squared is equal to this term. If you simplify, 1 minus half r over L squared multiplied by sine theta squared, and squared is equal to the square of 1 plus the square the second term minus 2 times by the first term times by the second term. So if you expand this term, you can extract that the square of this phrase is equal to this term. And for when this term is very small, we can neglect it. And finally, we can conclude that this phrase squared is approximately equal to 1 minus r over L squared times by sine theta squared, which this term in fact is the phrase under the radical. So here you can see. So by using this approximation, when this term is very small, we can conclude that instead of this term, we can substitute this square term. And when you substitute here, this squared will be cancelled out with a square root. And finally, we can extract the harmonics for this function. So by simplifying this, yt can be concluded that it's equal to r plus L minus r cosine theta. As you can see, instead of this term, we substitute from this phrase and simplify, because the power 2 will be cancelled out with the square root. And finally, once you simplify this, you can extract that yt is equal to some harmonics of theta, and 2 times by theta. Now we can substitute into the equation of motion. When you drive the equation of motion, and then we can extract the non-homogeneous term for this equation. So if you write the equation of motion for this system, as I told you, this system with degree of freedom xt, and if you, for example, use the Newton's second law and plot the free body diagram, when this mass m is going to the left, we will have some forces here, one force due to the springs, one force due to the damper, and all of them will have one negative sign because they are in negative direction of xt. So we will have k times by here, because both edge of the springs and damper are moving, so the force in the spring is equal to the stiffness multiplied by the difference between the deflection of two edges. One edge has the deflection of xt at this edge, and the other edge has the deflection of yt. So the force in the spring is equal to k times by x minus y when we assume this direction for the force in the springs. So for the damper, we have the same scenario. It's equal to c times by x dot minus y dot, and finally it must be equal to m times by x double dot, which is the acceleration. And once you simplify this, you can extract this equation as the equation of motion for your system. Now we have non-homogeneous term, which is a function of y and y dot, which y is calculated here. And now we can substitute that y is equal to this term. And once you substitute y is equal to this term, and also we need to calculate the y dot. Here you know that theta is a function of time. So when you calculate the derivative of y with respect to time, the first term here, r, is a constant. R cosine theta, the derivative of r cosine theta is minus r times by sine theta. And here again, these terms are constants, these terms are constant, and only cosine 2 times by theta will have the derivative with respect to time. So we can substitute and calculate, and finally we extract this equation of motion, and then we can substitute the numerical value for omega, L, R, and M, K, and C. And finally, we can extract the numerical form for the equation of motion and non-homogeneous terms. Is it clear so far? Any question? Of course, in the exam, if I give you any question like this, you are not supposed to extract this relation for theta and phi and yt. Definitely, I will give you the form of yt. For example, I will give you this information, this yt, the final form for yt, and then you are supposed to substitute into the equation of motion, and you are supposed to extract the equation of motion, this equation, and then substitute into the equation for y and y dot, and extract the final form of the equation of motion and solve it. Okay, so you don't need to extract these relations because these are some approximation, and in the exam definitely you don't need to extract these equations. Any question? Is it clear?
Yes, sir.
Okay. So the next step, we need to substitute the numerical value. Once you substitute the numerical value, you will see we will have the equation of motion in this form: mx double dot plus cx dot plus kx is equal to ft, which ft is this term. And if you substitute the numerical value, ft will be in this form. As you can see, this is the ft, the non-homogeneous term. As you can see, we have one constant part here, 10.25. We have harmonics with frequency 100, this cosine 100t, and also here we have sine 100t, and also we have harmonic with frequency 200, cosine 200t, and sine 200t. So because we have two different harmonics and one constant part, so the particular solution will include three different portions. The first particular response, xp1, for the xp1 for the constant parts, xp2 which is for the first harmonic, cosine 100 and sine 100, and xp3 the third part of the particular response, which is due to the second harmonic 200t. So the particular response for the constant part is a constant value C1. The particular response for the harmonic 100t is equal to C2 times by cosine 100t plus C3 sine 100t. And finally, xp3 or the third particular response is a combination of harmonics with frequency 200 with constant coefficient C4 and C5. We need to obtain C1 to C5 by substituting into the main equation. For example, for xp1, if you substitute into the main equation, the first derivative and second derivative of C1 is 0 because this is a constant value. So the derivative of xp1 with respect to time is 0. Once you substitute here, we will have k times by C1 because x is C1. It's equal to 10.25. Sorry for my bad handwriting. And from here, you can conclude that C1 is equal to 10.25 divided by K. So this is the C1, the first particular response, this one. For the second one, you need to calculate the first and second derivative of xp2 with respect to time. For example, the first derivative of this function is equal to minus 100 C2 times by sine 100t plus 100 times by C3 times by cosine 100t, and the second derivative will be equal to minus 100 squared times by C2 cosine 100t minus 100 squared multiplied by C3 times by sine 100t. So this is the xp2 double dot or the second derivative of xp2, and you can substitute into the main equation and then extract the coefficient of cosine 100t in the right hand side must be equal to the coefficient of cosine 100t in the right hand side, which is minus 10. As you can see, the coefficient of sine 100t in the left hand side must be equal to the coefficient of sine 100t in the right hand side, which is 100. And then you will have two equations, two algebraic equations with two unknowns C2 and C3, and then you can solve these two equations to obtain C2 and C3. For xp3 or the third particular response, we can do the same procedure and we can find C4 and C5 by substituting into the main equation and solving two algebraic equation, this time for the coefficient of cosine 200t and sine 200t. Okay, and then you can obtain C3, C4 and C5. This is the particular response, and the homogeneous response is clear. You can form the characteristic equation, which is m alpha squared plus c alpha plus k, and then you can obtain the roots for alpha 1 and alpha 2, and finally the homogeneous response or the transient solution is c1 times by exponential alpha 1t plus c2 exponential alpha 2t, and then c1 and c2, which are constant coefficients, can be obtained using the initial condition. But in this example, we only need to obtain the particular response and we don't have the initial conditions. Okay, any question? Is it clear?
Yes,
Okay. Okay, the next example, we have similar to the previous example, we have the same mechanism, but this time instead of a viscous damping, here we have a column damping. The base of a spring mass system with column damping is connected to the slider crank mechanism shown below. Determine the response of the system for a coefficient of friction mu between the mass and the surface by approximating the motion yt as a series of harmonic functions for m is equal to 1 kilogram, k is 100 Newton per meter, or the radius of this lens is 10 centimeter, and the length of the link is 1 meter. The coefficient of friction is 0.1, and finally the frequency of the rotation, which is 100 radian per second. So similar to the previous example, we can find the harmonic or a harmonic form for yt, and we can extract the harmonic base motion in the form of summation of two different harmonics. And then we can extract the equation of motion. This time we don't have viscous damping. We only have the column damping or friction force between the mass m and the surface. But when you write the equation of motion, again we deal with a non-linear equation of motion because we have friction. We have the sine function in the equation of motion. So to solve this equation, and according to this point that yt can be written as a function of some harmonics, so we can find an equivalent viscous damping form or viscous damping constant for this friction, and then we can solve this equation and obtain an approximation for the solution. So the equation of motion is mx double dot plus kx plus minus mu n, which is the friction force, and it's equal to k times by y. As you can see, here we don't have a viscous damper between mass m and the base. So in the non-homogeneous term, we don't have cy dot. We only have k times by y, and y can be substituted from the previous example, yt, and we can obtain the non-homogeneous term as a function of harmonics omega t and 2 omega t, or 100t and 200t. But here we rewrite, as you can see, we rewrite in the form of a viscous damp system. Instead of plus minus mu n, instead of this friction force, we substitute cx dot, which c in fact is a equivalent damping constant, and we need to calculate this by using the energy dissipated in each cycle and the equation for the column damp system. Here we know that the equivalent C is equal to 4 times by mu times by n divided by pi omega x, which x is the amplitude of the response. And once you substitute here, we will have the equivalency, and then we can substitute into the equation of motion. Also, we can calculate the natural frequency and the friction force, the normal force, which is mg, and then we can substitute into the solution, into the formula for the solution of a system with column damping. If we assume that the particular response 1 is C1, for the constant non-homogeneous term. The particular response 2, which is with frequency omega t or 100t, it has an amplitude of x1 and phi1, and the particular response 3, or the third particular response, it has an amplitude of x2 and frequency angle phase phi2 and the frequency 200. So we will have these three particular response. The C1 can be easily obtained from similar to the previous example. I mean, you can substitute into the main equation and obtain C1. But for XP2 and XP3, you need to obtain the amplitude and the angle phase by using these two formula. And once you substitute here, you can solve the equation for x1 and x2 and obtain the amplitude of the response and also the angle phase, as you can see by using these two formula. And finally, the total particular response, which is equal to xp1 plus xp2 plus xp3. Okay, any question? Is it clear?
Yes, sir.
Okay. Okay, the next concept is the response under a non-periodic force. This time we can assume that the system is subjected to a non-periodic force, and we will have a lot of different examples for this type of loading, and maybe in more than 50% of the cases in their practical examples, the external force is not periodic, and we need to find another method to solve and find the response for this type of systems and this type of loading. The purpose is to obtain the particular response when the non-homogeneous term has a general form or it's not periodic. For this purpose, in this course, as I told you in the introduction, we will discuss three different methods. The first method is convolution integral. The second method is Laplace transform, and finally the numerical methods. The numerical methods and Laplace transform will be discussed in the week 8, hopefully. But the convolution integral will be discussed in this week, and I hope we can finish this by tomorrow. And for this purpose, first we need to investigate the impulse response of a system, and then you will see how to expand this solution for a general loading to find the response of a system for a general loading. So the first step, we will find the response of an underdamped system subjected to an impulse. And here, from the dynamics, when we have impulse, we will have a change in the momentum of the system, or we can write the conservative of the linear momentum for a system, and we know that F times by delta t, which F is the amplitude of the impulse, multiplied by the delta t, which delta t is the period of the time, which during this time the impulse is insert to the system, or the impulse affects on the system. It must be equal to the variations in the momentum of the system, and the momentum is equal to mass times by the velocity. And in the other words, we can write that m times by x2 dot, which x2 dot is the velocity of the system or of the particle at the second condition or final position, minus m times by x1 dot, which x1 dot is the velocity in the initial condition. So this term mx2 dot is the final momentum, and mx1 dot is the initial momentum. So we call it delta G, or the change in the momentum, linear momentum of the system. Now the impulse of magnitude F, we can assume that is acting at t is equal to 0. So F is equal to F times by delta t, which you know that delta t from mathematics, you know that delta t is the direct delta function. And in the definition of delta t, you know that delta t has an infinity value at t is equal to 0, and it's equal to 0 for other times. Or we can write it in the general form, and we can find the definition, the general definition for the Dirac delta function, which is delta at t minus tau is equal to 0 for all of the times which are not equal to tau. So the integral of delta t minus tau from 0 to infinity of time is equal to 1. And if this function multiplied by f times by delta t or times by a function of time, the integral of delta t minus tau times by ft, which ft is a general function of time, dt from 0 to infinity is equal to the value of the function f at t is equal to tau. So using this integral and this equation, we will find the response of the system subjected to a general excitation or general external force. So these are only some mathematical equation that we will employ them into the system to extract the response of the system subjected to the general loading. So again, consider a system, a single degree of freedom system subjected to the load Ft, which this Ft is an impulse with amplitude, any arbitrary amplitude. Okay, we start with, for example, 1. For this system, the response for an underdamped system can be obtained using the integral, and we can obtain that xt is equal to this term. Here you can see which this is the response of the system for an underdamped system. This is the homogeneous response. As you can see, we have psi omega n, omega d, which is a function of psi and omega n. We have x naught and v naught, which are the initial condition. And finally, this is the homogeneous response. Now we can obtain the response and these initial conditions and the constant coefficient x naught and v naught using this diagram. Here you can see that at this point before the impulse inserted to the system, the velocity is 0 and also the displacement is 0. So we don't have any displacement or any velocity when t is less than 0 or before the impulse. If we assume that the impulse time is or the origin point of the time, so at t is equal, t is less than 0, sorry, or for the negative time or before this time, the velocity and displacement of this mass is 0. And in other words, the mass is at rest, initially at rest. But for t, after this impact, we will have the impulse, and if we assume that the magnitude or the amplitude of the impulse is equal to 1, from the conservation of the momentum, we can write the conservation of the momentum equation. We should conclude that the momentum before the impact, which is m times by the velocity at t is equal to 0 before the impact, minus m times by the velocity after the impact, it must be equal to 1. And from here, we can conclude that the initial velocity after the impact is equal to 1 divided by m, and the initial displacement will remain the same as before the impact, and it's equal to 0, because this impact or this impulse only affect on the velocity of this mass m, and it will appear as an initial condition in the velocity of mass m. So we can use this initial condition v naught and x naught into the response, and then we can simplify and obtain the response of the system subjected to an impulse, as you can see. So the response xt, which here we call it gt, which is in fact the response of the system subjected to the impulse, and we call it impulse response function. It's equal to this term, okay? And if you plot it, xt over the time, it has some behavior like this. Of course, all of these results are only for an underdamped system, okay? So for an underdamped system, if you plot the response subjected to an impulse, you can see it start from here, and In fact, this is 1 divided by m, and 1 is the magnitude of the impulse. And also, if we assume that the magnitude of the impulse is not unit, or it's, for example, f, which f is a number, then instead of unity, we can substitute f, and this is the response of the system subjected to an impulse with magnitude f, and it's equal to f times by gt. So we can obtain the response of an underdamped system which is initially at rest to any impulse. With this equation, you need only find the damping ratio psi and the natural frequency, and then you can easily find the response for any system subjected to the impulse. Now we can use this data to obtain the response of that system under a general loading. Any questions so far? Is it clear? Of course, we only extract some mathematical equations that you definitely, if you refer to your previous courses, you had these equations in the mathematics, but in that course, you don't know that what's the application of, for example, impulse. But here you can see that impulse, in fact, is an impact on your system, and the effect of this impact will appear as an initial condition in your velocity. So you can see here in this course what is the application of that mathematical equation, and I will explain that we will expand these results for a system subjected to a general loading, and then we can find, by using this equation, we can find the response of a vibrating system subjected to a general loading that can have a non-periodic and non-harmonic form. Okay, so any questions so far? Is it clear?
Clear, sir.
So another point that you know that we can move the delta on the time axis. I mean, from t is equal to 0, you can move it to the point, for example, t is equal to tau. Then you can assume that your origin point start from this point. I mean, you can assume that your origin point start from tau, and then the response is the same, but this time, instead of that the response start from here, you will see that the response start from this point. So you can, in the mathematical form, you can substitute, instead of f times by gt, you can substitute f times by gt minus tau, which this is the response of an underdamped system subjected to an impulse which is inserted to the system at t is equal to tau. So this is in terms of mathematics, you can write in this form, but in the physical meaning, you know that you can move your origin point of time from, for example, here you can move it to this point and assume that time start from this point. Okay, so it's up to you, but from the mathematical point of view, you can write in this general form. And tau is the time that the impulse is affecting on your system. Tau can be 0 and any other positive value. So you can write in this general form. Okay, we have one example, of course, because we don't have time. We can continue with this example tomorrow, and I hope tomorrow we can finish this concept. Any questions so far? If you don't have any question, we can wrap up this session and continue again tomorrow.
Hello, sir.
Hello? Yes?
Say we
No
the final exam will be online or face to face for 366?
The final exam, I'm not sure till now, but maybe it will be face to face. I'm not sure.
Okay, sir.
Okay, any other question?
Say for the short test,
The shortest
will there be any?
yes, will be shifted to the next Tuesday.
Okay. So will there be any derivation question?
Sorry? Any what?
Will there be any derivation question?
I cannot understand.
Do we have to derive? Do we have to derive in the short test as well?
The short test will be conducted on Tuesday next week at I think 8 or 9 p.m. And the rules and the type of